As we finish up Module 3 on Introduction to Confidence Intervals, it behooves us to look at one last issue, and that is actual sample size. As we work our way through these problems, what we've done is we've used X bar to predict mu. That is our goal, that we could take a sample and use the sample mean to predict the population mean, because we don't know the population mean. Now, the other issue is that we don't know the population standard deviation. So we're going to use S to predict sigma. And that is fraught with a few problems. S is a good predictor of sigma if the sample is large enough for S to converge on the value of sigma. As a rule of thumb, a sample of n equals 30 is considered large enough for S to converge on sigma. Samples less than 30 require that we exchange our Z confidence for what we call a t-score. And what the t-score does is it allows us to expand the effect size to compensate for the fact that S may not be a very good predictor of sigma. Now, the t-score allows us to expand the effect size interval to compensate for S being a poor fit for sigma. The t-score is calculated using two values. The first of these is the confidence level. Just like in z-score, we have a confidence level, say, of 95%. With a t-score, we have a confidence level of 95%. But the other thing that we do is we must calculate degrees of freedom, where degrees of freedom are defined as the number in the sample subtract 1. For example, a confidence level of 95% with a sample size of 16 converts to a t-score of 95% with 15 degrees of freedom, because the degree of freedom is equal to 16 minus 1, and we can extract this from the table. Here's a table, and I have included that for your class, but it's called a student's t-distribution. What it does is lets us look at small samples. Now, the first thing, we got a lot of information here. We need to unravel it. The very first thing we want to look at is this degrees of freedom and confidence level. The degrees of freedom go down this side, and the confidence level goes on that side. So in our problem, we have 95% confidence, and runs down ultimately to the z-score of 1.960. We then have 15 degrees of freedom, which allows us to home in on 2.131. What we have done with a t-score of 95 and 15 degrees of freedom is that we have expanded the 1.96 z-score to 2.131 to compensate for the fact that S may not be a very good predictor of sigma, and it assures us that we are still in the range that we need to be in. If the sample has less than 30, we use the t-score to replace the confidence. The t-score value is extracted using the confidence level and the degrees of freedom, where degrees of freedom is n minus 1. For example, a confidence level of 95% with n equals 16 converts to T for 95% with 15 degrees of freedom, which we saw in our table was 2.131. In order to calculate effect size, we put the t-score in place of z confidence. We use the t-score, multiply it by s over the square root of n, and it's s over the square root of n because we're using the x bar distribution. And our confidence level becomes x bar minus e and x bar plus e. Not much has changed. Now, I want you to keep climbing the ladder. You're almost off of rung 3. This isn't hard. All it is that if we have a sample less than 30, we use a t-score instead of a z-score. And the t-score is calculated with the confidence level and the degrees of freedom, where the degrees of freedom is the sample size minus 1. You've got this. Life is good. You're going to make this, and we're almost ready to really roar with this information.